I wanted to take a minute to go into a little bit more detail on how to use the HyperX bonded joint analysis tool on structures with more complex loading, for instance, spars bonded to skins, and just kind of show how that process works in the software. So oftentimes we can use the automated load extraction capabilities in HyperX, especially when we have a structural joint where the loading is relatively straightforward. And that would be things like structural lap joints, or tension under bonded reinforcements, things like that. But it is also important to be able to assess joints where the loading is more complex or where the boundary conditions are not as obvious for the software to infer automatically. And in these situations, we do allow the user to fully define the forces and boundary conditions that are applied to the joint just arbitrarily and use that to assess strength in these cases. So an example of this is the diagram here on the right of a bonded spar or a stiffener that's being pulled off with an embedded defect, an embedded crack on the right side here, as well as supports on either side due to other substructure. And in this situation, the user might prefer to just apply loading manually or directly. And that basically lets them apply this pull-off force while restraining the transverse boundary conditions and predicting strength with this embedded crack. So this is a process that we've done quite a few times pretty successfully as well. So that previous example, that spar pull-off, is actually something we've done as part of the validation of the tool. So the validation data we collected under the NASA Advanced Composites project included spar pull-off, and we did apply loading in this way to successfully validate the tool against it. Recently, we've been doing work with NASA on an unrelated project with what they call a Y joint, very similar to a pi joint. And so this is an example of the D8 aircraft. It's a concept aircraft currently in development with this double-lobed fuselage structure, including these Y joints with tension rods connecting the upper and lower parts of the fuselage. A zoomed-in version of that joint is shown here. And so as you can imagine, loading is quite complex with internal fuselage pressure and then pull-off, and then consideration of defects and all of that. And we did successfully demonstrate using HyperX to not just analyze, but also size and perform trend study analysis on the design of this joint. And that's all documented in this public paper I have referenced here, available online. So more specifically for a spar to skin joint and what that might look like, we have an example here on the right of a C-channel spar bonded to skins where there's internal pressure trying to push those skins away, and perhaps an internally embedded crack in the bond line. And so we can do this analysis in HyperX, and we would basically integrate that pressure and come up with equivalent boundary conditions to apply to the HyperX analysis. So that basically looks like a translation from the actual loading here on top to the equivalent loading that HyperX considers. So we make some simplifications, but we basically just boil it down to the most important details and apply the analysis to HyperX, and we get all of the same features that we have for the structural joints where the loading is pulled out automatically. So that means sizing of the joint, the laminates, the thicknesses, geometry, all the stress fields that are predicted, the VCCT analysis, that energy-based fracture mechanics analysis with an embedded crack. Of course, the analysis is still very fast, much less than a second for a typical run, and it's very easy to set up. It's very easy to process the results. And overall, it's just a good way to do this sort of analysis and trend studies and sizing.